Good morning. I'm Masaharu Kobayashi from the University of Tokyo. So first of all, I'd like to thank the committees for having me in this really exciting symposium. So originally, I was asked to talk about the negative capacitance FET, but I'm also doing some ferroelectric memory as well, so which may be interesting in terms of energy efficient electronics. So I set a title like this, and I'm going to talk about the impact of ferroelectric hafnium oxide for logic and memory applications. So let me start. So I'm not going through my self-introduction, but I remember the last time I visited Berkeley. It was a football game in 2008. So I was with my friends in Berkeley, and at the time Stanford lost. So I was so upset. So that's why I clearly remember the last time I came here. Anyway, so I started my laboratory back in 2014. So I spent about 3 years already. So I'm going through my research activities. So this is the outline of my presentation. So first, I'd like to talk about the general challenges for ultra-low power IoT devices. And I also talk about the kind of discovery of ferroelectric hafnium oxide from German group. And I'm also going through the logic and the memory application using this material. And finally, I will summarize my presentation. So as you know, Internet of Things, IoT edge device has been playing a key role as a sensor node device with wireless communication. And the number of these kind of IoT devices become trillions or even more. So obviously, it must be ultra-low power. And ultimately speaking, this kind of device must operate by generating its own power using, for example, energy harvesting technique. However, in some environment, like in room, the available energy may be really limited, like a human vibration or environmental radio. And it's as much as 1 microwatt. So if you go to the electronics shop, the available commercial sensor node device consumes like a 10 microwatt, 100 microwatt. So we probably need to reduce the power consumption by more than 10 times from now. So I'd like to tackle this challenge by some new device technologies. So to figure out what device technology we may need, so let me take a look at the microcontroller unit. So this figure shows the ballpark power consumption of MCU versus active rate. So active rate means how many times our transistor switches per second in average. So as you know, at the high active rate, the dynamic power is dominant, while in a low active rate, standby leakage power is dominant. So IoT device is supposed to operate in an intermittent mode, so the active rate should be low. So in that case, the power consumption is limited by leakage current. So, to reduce the power consumption, the first approach will be high ion-IOF ratio transistor, such as steep-stop transistor, so that we can reduce the IOF, but without degrading ion. And the other approach may be just to power off the module as much as possible. So as Professor Hanyu mentioned yesterday, so we have to, but to do this, we have to store the data before the power off. And when the power on, we have to record the data without much overhead. So this is so-called anomaly of computing, and non-volatile memory will play a key role. So these are the two approaches I'm thinking of. So for the high ion-IOF ratio transistor, so there are several candidates, as you know. So one is a TFET, which was intensively discussed yesterday. And the other is a negative capacitance FET NCFET, which was invented by Professor Salafuddin, which is a really exciting idea. So the key idea was explained by Professor Januszki yesterday. The key idea is basically to introduce a negative capacitance in a gate insulator and make the body factor less than 1, and subthreshold slope become 60 millivolt less than 60 millivolt per decade. So, so we can realize this negative capacitance by ferroelectric material. So the ferroelectric is important. And for anomaly of computing, there are several architectures, of course. And if we implement anomaly of computing by using conventional architecture like a CPU, internal SRAM, peripheral bus, and then flash memory, then store and recall operation is very slow. It's a very long latency. It's power hungry. So the idea is basically we have to have very low power non-volatile memory, and we have to move the non-volatile memory as close as possible to the CPU core. One approach will be like MRAM. We can use the non-volatile memory as a working memory, but it requires high reliability and also it requires a new interface. So, but as a hybrid approach, we probably can give the non-volatile functionality in the SRAM. Of course, it's non-volatile SRAM, NVSRAM. But of course, the SRAM is big, so the capacity is probably not too high. But the IoT device may not require such high capacity depending on the data rate and the communication. Well, moreover, the SRAM is really fast, so which is good for intermittent operation. So I think if the process cost is met, NVSRAM can be a promising solution for the low power IoT. So let me jump into it, I like to have ferroelectric based NVSRAM. So okay, so ferroelectric is great, but I got to figure out, I got to understand that it's a challenge. So the challenge is a process, basically CMOS compatibility of this material. So usually perovskite type material has been used, but the problem is perovskite material usually designed really thick, and also it requires a rare earth metal electrode, which is really hard to pattern. And also retention and endurance are also another concerns. So these are the kind of challenges for the conventional material. But luckily, recently the ferroelectricity has been discovered in the hafnium oxide thin film, which has been already used in the CMOS technology, and it's already mature. So what's good for this material is it shows the ferroelectricity with less than 10 nanometer. It's really thin. And also you can use a very typical ordinary metal electrode like a titanium nitride or tantalum nitride. So it's easy to pattern. So this material is CMOS compatible and it's scalable. So I believe this material will open a new path for the ultra low power logic and memory application. So that's the key idea. So let me briefly touch on the origin of ferroelectricity in hafnium oxide, which was discovered in German group. So of course there are several debates now, but the major consensus is this orthorhombic phase appears by doping some element in the hafnium oxide film. Then ferroelectricity appears. Another thing is, unlike the perovskite material, basically oxygen anions are responsible for polarization. These are the unique feature for this material system. Okay, so based on this background, so I'm going through some activity of a negative capacitance FET using ferroelectric hafnium oxide. So my first interest was at how low voltage NCFET can operate. So that's my first interest. So I studied modeling and simulation for the low voltage NCFET. So the device structure is just a planar FET targeting 0.2 volt operation. It's maybe ridiculously too low, but I targeted 0.2 volt. So this graph shows the ion-I-off ratio contour plot as a function of remnant material parameters, remnant polarization PR, and the coercive field EC. So luckily, there is a process window even at the 0.2 volt. And if you look at the right figure, this figure summarizes the experiment, kind of survey result of experimental data of hafnium oxide ferroelectric capacitors. And you can see that you can choose the appropriate parameters from the ferroelectric hafnium oxide material. So that's great. So it's really, we can choose this material for the low voltage operation. And the second interest is how fast this NCFET can operate. So as I learned from the undergrad solid-state physics from this book, the atomic polarization can respond up to microwave frequency. So this may limit the operation speed of NCFET. So I just simply included some time dependence in my model, and I simulated surface potential versus gate voltage as a function of sweep time of the gate input. And this result summarized the hysteresis voltage as a function of normalized sweep time. So suppose like 100 picosecond time constant of polarization switching, and NCFET can operate faster than 10 megahertz, so which is good for IoT application. So the next interest is the scalability of this material. So I was wondering if this kind of negative capacitance gate stack can fit into advanced CMOS technology. It's a gate-less process, and it has a very narrow trench after pulling the dummy gate. So I was wondering if it can fit into this technology. So this graph shows again ion-I-off contour plot as a function of ferroelectric thickness and interfacial layer thickness. And again, luckily at 0.2 volt, there is a process design window. So this system can fit into the gate-last process in 10 to 20 nanometer gate range. So this is also good. So, but the question is, so I did some simulation on the operation speed of NCFET, but the question is how real it is. So I just assumed the 100 picosecond time constant, but I was wondering how real it is. So the next interest is to experimentally extract the parameter which governs the dynamics of NCFET operation. So basically, the model is usually based on Landau-Cartonic equation, and here's the dynamic term, and this is the parameter rho, which is kind of important parameter. So I fabricated a ferroelectric half-indium oxide capacitor and built a simple measurement system and analyzed the data and extracted parameter rho. And again, simulated transient characteristics of NCFET. So again, the NCFET can operate faster than 10 megahertz, which is again good for IoT application. So, but the one thing I wasn't really satisfied with my model is fitting accuracy. So far, my model is based on a single domain model. So this graph shows one of the example of transient current response to the step input. So the modeling fitting accuracy wasn't really great. But now we introduced a multiple domain model, and which improves the fitting accuracy very well. So now I'm rebuilding my NCFET model by multiple domain now. Okay, so the future of NCFET. So as Professor Ionescu mentioned yesterday, I also think that the future will be the kind of fusion with other steep slope transistor like a TFET. So just to recap, substantial slope is expressed by two terms, transport term and a voltage divider term. So this term can be improved by TFET, and this term can be improved by negative capacitance. So as the Professor Ionescu mentioned yesterday, negative capacitance can be an additive booster. So if you can combine TFET and a negative capacitance, we should be able to achieve some sort of super steep slope transistor. And we did some modeling and simulation of this system. And if we can carefully design the NC TFET, the substantial slope can be improved in a very wide range of current. And energy efficiency can be improved by more than 10 times. So that is great, and it could be the future for the negative capacitance FET. So, so for the rest of the time, let me go through our recent activities on the memory application of ferroelectric half-indium oxide. So there are several architecture. Yeah.
I wonder what is the voltage potential that you think is possible? Can you go back?
Sure.
So what voltage? No, not all the way back.
All right.
Let's show your IV curve again. And
A IV curve.
What is the potential low voltage that you think can be achieved?
Well, so just ignoring the variability and also statistical variability, I think 0.2 volt seems to be doable. But of course, I ignore several really detail in the model. So regarding all these components, I think a 0.2 volt may be, feasible. I think. Okay, so there are several architectures for NVSRAM. So actually there are many, as probably many of you know, there are several many researchers back in 90s and also early 2000. So there are several architectures were proposed at that time. So for my study to understand the feasibility of this technology, I choose just a very simple one. It's a two-cell NVSRAM, so which consists of 60 SRAM with a 2 ferroelectric capacitor at the nodes. So this capacitor memorizes the polarization at each node. And so the operation principle is like this. When you power off, you can basically raise the plate line to VDD and pull down to VDD, pull down to ground, so that you can memorize the polarization state in here. So this structure architecture has a simple operation and a simple integration scheme, and also moderate operation margin. And of course, this is SRAM, so it's big. But what's good is it operates as SRAM in the normal operation mode, and it doesn't need to flip the polarization every time. So it's not a destructive readout. So the only time you need to flip the polarization is when you power off, and then power on. So the reliability endurance may be mitigated, requirement may be mitigated for this architecture. And also, so that's the idea. Right. So students and I started investigating this structure and we fabricated a prototype of the NVSRAM with a ferroelectric half-inch oxide capacitor like this. So this is a microscope and these are the capacitors. So here's the cross-section TM of the ferroelectric capacitor here. It's a 9 nanometer thickness and it's uniformly crystallized. So we tested the functionality of this NVSRAM, so as well as SRAM fabricated on the same chip. So what we did was basically first we write the data 0 or 1 and precharge a bit line and read the data for confirmation. And we store the data before power off and we wait for the arbitrary time for during the power off. And when we turn on power on, then we record the data and then precharge a bit line and verify the data. And from these results, we were able to store and record operation in the NVSRAM. On the other hand, SRAM just erase the data when it's power off, and when power on, it becomes just a state which is determined by the characteristic variability. So this is a kind of demonstration of an NVSRAM with ferroelectric half-inch oxide. So let me a little bit touch on the reliability. So here is the retention, and here is the endurance characteristics of the ferroelectric capacitor. So from our capacitor results. So I expect more than 1 year retention and also 10 to the 8th endurance cycles. But of course, for the practical use, we need to guarantee 10 years retention. But for the endurance, probably endurance requirements may be mitigated for this kind of architecture, as I mentioned before. So, for example, if we power off and power on this NVSRAM every 1 millisecond, we probably just need a 10 to the 9th reliability or endurance cycles. But anyhow, we will need a further development for the 10 years retention and such, reliability requirements. Okay, so let me summarize my presentation. So I talk about the device technology challenges for ultra-low power IoT application. So higher ion F transistor and normally of computing will be two approaches. And I believe that ferroelectricity, ferroelectric half-inch oxide will open a new path even for negative capacitance FET and also nonvolatile SRAM, importantly at low cost. And lastly, I'd like to thank my lab members. We are a very small troop. So we just have 2 students, a master and doctor. So I really appreciate their hard work. And also I'd like to thank the government funding and also partners. Thank you very much for your attention.
We have some time for questions. Uyghur.
It's okay, I have 2 questions. First one is related to the time measurements. 10 megahertz, again, I think there's still a discussion going on related to this. You're suggesting 10 megahertz is about the time you think the fastest it can do. I would suggest that industry wants to see more than gigahertz. Mm-hmm. So can you comment on that? And Saif has some work suggests it's faster. Yeah. Can you comment on why are some differences in understanding in this area?
Well, I think it depends on the assumption experiment data for the modeling. So I just pick up the typical number from the I don't have a capability to measure really fast measurement. So I just refer to some old papers and then get the number from the time constant, and it gives sort of kind of 10 megahertz, 100 megahertz range. But probably depending on the material system and also the time response that the device has, it should be able to go up to 1 gigahertz, I think. Yeah.
Okay. The second question is related to the SRAM, non-volatile SRAM. Can you tell us the potential you used? What was the voltage of the operation for your experiments?
That's a good question, and I didn't really fully investigate the voltage range because one of the problem is, so 60 SRAM has a little higher voltage than the logic transistor. And also, we have to add some variability for this ferroelectric capacitor. So that will, probably we have to add some more margin to the 60 SRAM. So I think that for this kind of memory, I suppose like a more than 0.5 volt operation. 0.5 volt may be too aggressive. So like a 0.6 or something like that.
Jeff.
Okay. Oh, got Eli's mic. I'd like to ask a little bit more about endurance requirement. So you put up an endurance requirement of 10 years, which is kind of a standard number everybody puts up for memories, but this requirement is really driven by storage class memory, like hard drive.
Right.
And the application you're talking about, like for power management, presumably this requirement may be a little over-specified. What is your opinion or knowledge, what can you say about what would be retention time requirement for the power management application?
Power management for the storage class memory.
No. So in the application you're discussing of having the backup memory for
right.
SRAM for power down. Right? And then presumably you don't power down, in an IoT application, you presumably don't power down for 10 years.
Right.
So what is your, have you any insight or comment about what might be a more realistic retention requirement for that application?
I see. Well, I think the retention, I think we require 10 years retention. But for endurance, maybe a little bit different, I think. Because as I mentioned, this time, well, depending on the architectural memory, this architecture doesn't really flip the polarization every time. It's just like once per 1,000. So it's very much less, I think, flip polarization reversal. So as I said, for example, 1 millisecond power off every time, then that's probably just require, it doesn't require 10 to the 12 or even 10 to the 10th. I think in this case, I guess 10 to the 9th may be fine.
Yeah, so that makes complete sense to me about endurance requirement, but why do you stick to 10-year retention requirement?
Oh, that's for customer. Customer satisfaction.
Okay, all right.
Okay, you have one question?
Yeah, a quick one. How is it that a material that is as well studied as hafnium oxide, suddenly people discover it's a ferroelectric? And what was this magic metal that you put in to make it ferroelectric?
Well, many. So as probably many people know, we can dope any kind of metal. That's really interesting. And I don't think it's fully understood yet. So you can dope zirconium, and not like just zirconium, you can dope aluminum, silicon, scandium, or whatever material. So it's very interesting, but not fully understood yet. Yeah, but zirconium seems to be good for low power, low temperature process. But for the reliability concern, you should stick to silicon or aluminum doping, I think.
Now, in your view, there's a controversy whether it should be multi-domain ferroelectric or single-domain ferroelectric. Can you tell us what your view is on that?
Oh, that's a tough question, I think.
Yeah, let's take that. Let's take that offline in the interest
of
time.
Yeah.
So let's thank Professor Kobayashi again.
Thank you very much.